Okay, my name is Ryan. I'm a PhD student at the Kaplan Institute in Groningen. I work with these various people, my main supervisor being Karina. And I'm going to talk a little bit today about the work we did looking for high-redshift outflows with JWST medium resolution spectroscopy. I will start a little bit by explaining why we want to study outflows. We've seen this figure already this week, but the idea is that if we look purely at theory and then compare straight to observations, we find that at both the low mass and the high mass end, we don't recover the number density of galaxies that we would expect. And we know at this point fairly well that stellar feedback is one of the main reasons this happens at the low mass end, and then at the high mass end, AGN become much more dominant. But we would really like to know exactly what's going on at high redshift in this low mass regime. One of the other main reasons we want to study this, especially now, is we're getting a lot more observational evidence at this point that at high redshift, star formation is very stochastic, and it follows this cycle of going into a burst of star formation and then a phase of reduced star formation. And we really want to understand the mechanisms that are causing this type of behavior and whether stellar feedback alone is enough to regulate this process. I want to address very quickly the most obvious question, which is that JWST has a very, very capable IFU on board. So why, when you have that opportunity, would you try and do this study with the multi-shutter array, which can only produce one-dimensional spectra? The most compelling point for this is to compare observations from both types of instrument, or both modes of spectroscopy. And you can see that for reasonably comparable observation times, the number of objects with the MSA is a magnitude higher, in some cases even more. And JWST time, as many of you know, is incredibly valuable. So when we start to put in proposals for the IFU, we really want to know that what we are targeting is interesting. We can't just blindly select galaxies that perhaps have no outflows in them at all. So being able to identify them with the MSA first is a good step to guiding what we want to look at with the more valuable IFU time. There has been some success with this so far. I will run through very quickly how we detect these objects with 1D spectroscopy as opposed to the IFU. We can take a very typical emission line that is broadened through normal thermal effect, and we can run through a couple of scenarios. The most extreme of these is sort of biconical broadening, where you see this broadening on both sides of the line that is very typical of an AGN, especially if it's observed in the Balmer lines. You have also broadening that can be driven from rotating clumps. If they are of similar mass and similar luminosity, you end up with sort of two Gaussian peaks that are of similar amplitude and similar width. And what we're interested in is this asymmetric broadening, with a small caveat that outflows can be biconical too. But we, in this work anyway, look very specifically at broadening towards the blue shifted end of the spectrum, which is indicative of gas flowing towards us. And I have a couple of examples here. Here's a very nice AGN example that shows the biconical broadening. And then here is some examples from our work that sort of preference this asymmetrical broadening. I will mention very quickly that there has been success with high-resolution spectroscopy prior to this work. But there are a few things working against us, mainly instrumental broadening and the fact that the spectral resolution of the medium resolution is quite a bit lower. But if we are optimistic, we have sensitivity on our side, and also the fact that the actual resolution of NIRSpec is generally higher than this proposed value. So With a little bit of care, we can probe sort of higher outflow velocities than the high resolution spectroscopy can, or rather we can't reach the same lower limits. These are our initial results. We found 40 outflow candidates out of 1,000 in total, which is, compared to other high redshift studies, quite low. Again, this is down to the limitations of the instrument. But in the local universe, it's reasonably comparable. And you can see from our plot that we cannot go below 200 kilometers per second. You lose that information to instrumental broadening completely. There is a diverse range of redshifts here and outflow velocities, and there is seemingly no correlation here. We don't expect one, so nothing to worry about there. We can also look at where they are in the stellar mass star formation rate. We find a lot of them lie above the main sequence, and this fraction increases with redshift, but again, this is sort of to be expected, as we've already heard today. The fraction of galaxies that are experiencing a starburst typically increases with redshift, so we are not worried about this. This is very normal. And it sort of builds up this property that the outflow hosting galaxies themselves are very, very normal, and we are just catching them at the time that they are exhibiting their outflow. We can also compare their outflow velocity to some of their physical parameters. There are no particularly strong correlations here, which at lower redshift we do see correlation with SFR, which if you are very, very optimistic, you can sort of see here, but I'm not, so we'll disregard that. We ultimately need a higher dynamic range in all of these parameters to really diagnose if there's any correlation here. The correlation with star formation rate is, of course, the most physical, because if you have more star formation rate going on, you have more stars to turn into supernova and eject gas from the galaxy. With that in mind, we can comment a little bit on how these outflows affect our galaxy. The first thing we want to know is whether the gas that is being expelled actually escapes the galaxy, which we can do by estimating the escape velocity of the galaxy and comparing it to the outflow velocity. And we find that for the majority of objects, this gas does not escape. It falls back in over some amount of time. And despite this, there not being any loss of material, the motion of moving through the galaxy itself is going to have a huge effect on this gas. It's going to heat it. But then once it leaves the galaxy and enters the CGM, what happens to the gas then is hard to predict. If the CGM is particularly cold for whatever reason, the gas could in fact cool down, and as it comes back into the galaxy, it is cooler than it was when it left, which could promote star formation in some way, whereas if the CGM is particularly hot, then the gas comes back and it can't be used, so then you suppress your star formation. We can also talk about this mass loading factor, which we've heard about already. And we find that the majority of objects transport gas at a rate that is greater than their rate of star formation. What this means is that as the star formation is ongoing, the galaxy is essentially losing material, which can lead to a short-term reduction in star formation rate. I don't want to use the term quenching because that's not what's happening. It is simply a lowering of the star formation rate. The star formation doesn't turn off at all. It just decreases, which is in line with what we expect in terms of observations. So for sort of a complete picture, we have ionized gas, which is expelled from the galaxy through star-forming activity. The gas returns to the host, and what happens to it depends entirely on the CGM. There can be heating, there can be cooling, we don't know. But the loss of material is very, very minimal, so any long-term quenching is probably not going to happen. This requires merging and AGN feedback and all of these things. But it is possible that they can temporarily reduce star formation in line with the stochastic star formation histories that we're seeing. And I will leave you with my conclusions. Sure there. Yes, with specific star formation rate, again, we don't see very much. This is probably also a problem of dynamic range. With the mass loading factor, there is a correlation, but it is hard to disentangle from the fact that star formation rate is included in the definition of mass loading factor. So yes, my last point here, that we need more objects would really help with these things.
Yeah, the second question is that it seems to see that you're seeing that the galaxy star formation not totally quenched, but there's just a decrease, which is the same thing that we need in order to, for example, to explain high-redshift galaxy that we have been modeling, and would require this gentle drop.
Mm-hmm. Thanks.
Yes, go ahead. How did you estimate the escape velocities of your targets? Like, did you estimate diameter mass?
Yes, very, very crudely. We don't have the data we need to be very precise. Off the top of my head, I cannot remember, but I can dig through the paper and tell you if you're interested.
No more questions? Thank you again.
Thank you.
We go to display and then change this.
Huh? Why?
Change the screen.
Thank you. Okay. Okay, can I start? Okay, hello everyone, my name is Maria, and I'm going to present some result of my project thesis, Unveiling the nature of a representative sample of the Extreme Emission Line Galaxy at intermediate redshift. We can skip the introduction because it was successfully completed by Patrick. Thank you very much. So we already know that distant star-forming galaxies are super important, but their low brightness make detailed study challenging. For this reason, the best strategy is to study similar galaxies but closer, and in this context arise the Extreme Emission Line Galaxy, which are characterized by the extreme emission lines like H-alpha, oxygen-3, and oxygen-2. They high equivalent width, low stellar masses, and gas phase metallicity, and high specific star formation rate. Here we can see a phase color composite of some ELGs from Van der Weyde et al. And in this plot, we can see the typical spectra obtained from Onodera in this type of galaxy, where this point of here are the emission line, at this line, some sky residual. Our main goal in this thesis is the study of the main properties of extreme emission line galaxy at intermediate redshift. For this purpose, we use the extended growth street from candles. Here we can see the coordinates and the regions covered by the two cameras. And in this box, some of properties of this field. In this study, only include those objects with signal noise bigger than 3 in the I, J, and H band. So we work with 28,000 sources. Our selection is based on the color criteria following by Van der Wel et al. We use this constraining, and we remove the sigma parameter in order to be more flexible with the criteria and obtain more possible candidates. We represented this in this color diagram, and we obtained this first sample of candidates. In other words, we was selecting those sources with unusual exit in the J band. The next step was removing spurious sources and allowing those sources that could be H-alpha emitter, oxygen-free, and oxygen-2. So the final sample that we were is 123 candidates. The morphology is super important as well for understand more about the galaxy evolution. For this reason, we use the catalog of visual morphology by Huerta's company, which is based on the definition from Carter-Tepe, who classify the galaxy as spheroid, disk, irregular, point saucer, and unclassifiable structure. In this slide, we can see some of sources of our sample in black and white footprint from Rainbow database. After classifying them, we obtain most of them are type spheroid, 3 disk, and 1 irregular. Here we can see the orientation of the images, the size, and some example of this type of galaxy. As we mentioned before, the equivalent width is important. So we estimated using this equation with a parametric value. We representing using this plot, where here there is the sample of H-alpha, oxygen-free, and oxygen-2. We compare the oxygen-free with Van der Wel, because Van der Wel obtained only an oxygen-free candidate. And we obtained this histogram, where the difference is due to the flexible selection criteria. And despite of this, we obtain a compatible result. Using the catalog, we can obtain general properties like the magnitude, mass, redshift, effective radius, and the equivalent width for the both sample, H-alpha and oxygen-free. We not include oxygen-2 because the small sample size. So the result here is that we obtain similar property for both candidate sample, and the interval range is near to the cosmic num. 9 of our oxygen-free candidates were observed using the KET and the multimirror telescope by TAM, which provided in order to we can obtain more information about this galaxy. As we can see, these galaxies are characterized by their extreme emission lines and the continuous very noisy. Also, we can see the nitrogen are very weak. That we expected this because in this galaxy have a low metallicity. So with this information, we can confirm that some of our candidates are ELG and nurture. As we mentioned before, the nitrogens are very weak, so we can use the BPT diagram. We need another alternative in order to study the ionization mechanism. So we use the mass excitation diagram, and we represent it like this with these two regions. We use the spectra mentioned before. We found 4 sources in the AN and 5 in the star-forming region. So although most are consistent with the star formation, the presence of agents cannot be excluded, and we need more spectroscopy. For this reason, we carry out a spectroscopy follow-up using GTC on April, where the main goal was confirm the redshift of the candidates and measure the emission line. We build the sample using those sources showing oxygen-2 and oxygen-3 in the A band. We can build a final sample of 16 galaxies. Although the analysis is still in progress, we could confirm some redshift of some candidates. All these results in this thesis will serve for Mosaic, which is a multi-object aneuploid spectrograph, which will be installed on the Extreme Large Telescope. The first slide, maybe, it will be around 2030. We could use its exposure time calculator in order to compare with another instruments. If, for example, we use it with these bands, with half a 26 in the continuum, with Osiris at GTC, we will obtain a signal noise equal to 3 in like more than 60 hours. Instead, with Mosaic, we obtain the same signal like in 3 hours, which is less much time. So here there is a summary. For future work, we have to complete the analysis of the observation and compare them with ELG sample at different rates. Thank you.
So from what I could see, most of your sample is O3 emitters.
Yes.
Why do you think that is?
I'm not sure, but some study obtain the same, that more of them are oxygen-free, but I'm not sure why.
No more questions? Okay, thank you again.
¿Esto funciona? Oh, Jesus. No. Okay. Okay, after this setting, hi everyone, I'm Antonio Jimenez, PhD student on the IAA, and today I'm here to present my research on the JWST survey for the first identification, physical properties, ionization efficiency of Extreme Emission Line Galaxy. I don't have much time to go into detail, but I'm going to try to do it the best as possible. No, obviously this is not working. Okay, so as Maria said, Extreme Emission Line Galaxies has high specific star formation rate between 10 to 100, and also extremely low metallicity. We can see that they are in the tail of low metallicity, 7.6, 7.4. But study extreme emission line galaxy is important because we can see in this plot from Maceda 2022, there is a huge increase in the fraction of extreme emission line galaxy when we go to high redshift. And this is the opposite that we see at the local universe, because in the local universe there is a weird population. This is a weird population. It only accounts for the 0.2% in the total Sloan sample. So this is getting important when we go to high redshift. Okay, to put more on the table, we have also that extreme emission line galaxy usually has broad components, and this broad component normally correlate with the fraction of the Lyman continuous photons. So this is a clear reason to study this population. Why? Well, the answer is easy. Is because high redshift galaxy has the same property as this low redshift extreme emission line galaxy. So they are the perfect laboratory to study all the physics in detail and then move to high redshift. Extremely metal poor galaxies have been detected already with the JWST. Here we have some references. There are two different ways of looking for these galaxies. We have the photometry and the spectroscopy. Photometry, as Maria said before, we can use the broadband photometry to do some color cuts. But for me, what I'm going to do is to use the JWST survey, that is photometry, but we have 74 narrowband filters. So it's like a pseudo photospectra. And this, I'm not going into detail with the JWST survey now, but the key point is like we are going to cover 8,500 degrees with these 54 narrowband filters. So there is no body of JWST here, so I'm going to skip all the details of the telescope. If someone is interested, I can provide later. And right now we have 30 degrees of the sky, but they are private. In the public data release, you can find 18, and these are the fields in which you can find all the filters measurement, all the 54 band measure for the objects. Okay, the key point in JWST is, as I said before, we have the images, we have the photospectra. We can see here, we have the oxygen 3, we have H alpha, we have oxygen 2, we can see barely the H beta, and this is compared with a DESI counterpart. Okay. Also, we don't have any bias, neither a selection function, so this is powerful. We just scan the sky. Obviously, we have the bias in the magnitude. This is the magnitude limit in the I band of Sloan, and all the photometry is based on this band. Okay. So how I look? Basically, I fit the continuum. I try to see the X-set flux compared with the adjacent bands, and following this formula that we have here, that is the flux at the line minus the flux of the continuum, has to fulfill this relation. And you can find more detail in Iglesias Paramo et al. And doing that, and applying more criteria, but doing that, we have found close to 1,000 galaxies. Close to 1,000 galaxies that has equivalent width greater than 300 angstrom. Okay, this is our criteria to say that this is just an emission line galaxy. This is the distribution of the sample, and here we show the photometric redshift compared with the DESI counterparts. We can see that it's a perfect one-to-one line, so we are really proud of this plot. Obviously, it's easy because we have we have 54 bands. So, okay. Later we apply the Seagull. Thank you, Dennis, for the code. And here we have an example. We not only use the JPass band, but we also use Galex, Sloan, Spitzer, and WISE, and using the parameter that we can see on the top. And with the Seagull, after that we have a lot of information, and here we can see the main sequence of the galaxies, star formation rate in the first 10 megayears versus the stellar mass, and we see that, well, each line corresponds with different main sequence at high redshift. And we see that our samples is in the main sequence of high redshift galaxy. So we are trying to go to this, that these galaxies are the local analog of high-redshift galaxies. Okay? Each red point is the DESI counterpart that we have found. And obviously, we can compute a lot of things, and one of them is the fluxes. We see a perfect align with the DESI counterpart. I say DESI counterpart because it's like the way that we have to say that, okay, our results are consistent. So we see that the fluxes that we derive from the spectroscopy and from the photometry are quite good. You have to take into account a lot of things because some lines could be blended in one band, but we have managed to do it, I think, quite well. Linking now this with the reionization epoch, we have this formula. I refer everything to Patrick and Laura's talk, but we are going to compute this factor because this is observational. There are the luminosity function in the ultraviolet there. This we are going to put to 0 because, as Laura said, there are no. It's assumed that it is like a 5%, so there is no more change. And this is the thing that we have to compute. So this is the result. Again, red line is our result, and different gray line are different relationships that have been found in the literature. But let's stop a bit. In the x-axis, we have the equivalent width of oxygen 3 in res frame, and in the vertical axis, we have the psi ion. So if we find that this trend, you can see that the scatter is not quite big, and we are following the same relationship at high-redshift galaxy. We can see here Janina's data, for example, from 4 to 10, or Paul from 1 to 6.7. And there are some caveats on this plot because it's not easy. There are a lot of physics involving this, the calculation of this number, and one of them is the attenuation law that we have to choose: Calcetti, FNC, Cardelli, and there is not a common frame for computing these things. So we try to do the best as possible and use Calcetti because everyone is using Calcetti. But for example, you can see that here there is SMC and change, and the values can change in a 0.3x. So anyway, it's more scattered, but the relationship is there. And finally, linking this with the youngest galaxy, there is also a trend of the psi ion with the H beta, because the equivalent width of H beta is highly correlated with the H. So that makes sense and indicate that are the youngest galaxies that produce the maximum ionization photon. And if we think in the high redshift galaxies where the star bars are more common, we can say that we have younger galaxies. This makes and reinforces the idea that maybe these local analog are really the analog of the high redshift galaxies. So I've been super fast because I don't have time, but those are the conclusions. And finally, thank you, because I'm coming from Granada, and this is the most representative thing that we have in Granada. So thank you very much. First of the second.
Yeah, this one. So you said that the given specific star formation rate, the EFGs only represent a tiny fraction of the galaxy, right? So can you tell at the given specific star formation rate what makes this galaxy to be an EFG rather than not, compared with another galaxy which has the same specific star formation rate? So what are the properties deciding whether the galaxy is an EFG or not?
Well, to be an LG, the physics of the gas has to dominate the physics of the galaxy. And so basically you can have, you can have a star formation, but if you have an old population, for example, will influence in the continuum and will reduce the equivalent width of the galaxy. So filtering by equivalent width, we are making sure that we are in the, maybe not the first, but the second star bars of the galaxy. I don't know if this answers your question, but Okay.